G'day, this is lesson 1 for unit 2 in data. Today we're going to look at a way of organizing some of the things we've been doing already and some new stuff. We're going to organize our thoughts and counting using what's called Venn diagrams. Most people have seen Venn diagrams. There's a funny example if you've seen the movie The Fault in Our Stars or read the book. It's in the book as well. Where there's a Venn diagram. You can look that up if you want. Here's a classic example. We've got three circles here. Each circle represents a set or collection of ideas, in this case, the environment, society, economy, and they overlap or intersect, we would say in math, in certain ways. And in this case, all three of them overlap here. And they've used this idea of sustainability. We're going to look at some sets where you get three sets in Venn diagrams, but you can have more than three, you can have less than three. You can make up your own and come up with funny things like that, but basically we're going to answer this question today: how can we organize outcomes using set and Venn diagrams? So you've got the handout. I would fill this out as we go through. Here's a very, very simple example, but it's just basically an idea to explain Venn diagrams. So given a six-sided die, how many outcomes are even numbers? So six-sided die, how many outcomes do you get? How many are not even numbers? Represent this using sets and Venn diagrams. So let's do that. So the first thing here is, let's call set A, so a set of numbers. Sorry for the awful scribbling. And I've got the set of numbers, so let's say A are the even numbers. So I've got 2, 4, and 6. So I can use that, if I call the set even numbers here, obviously, to create a Venn diagram. Well, we obviously are going to have a circle, and my circle is going to be really awful because I'm writing on a tablet. Yes, that's really bad. And we would call this set A. And so within set A, you can write these down. You don't have to. It's got these numbers, and these numbers fill this circle. So those are our even numbers. Outside of this, we've got everything that A isn't. So generally that's represented by a square box, and below we're going to have better representations of that. And so everything that A isn't, we call A prime or A naught. So it's pronounced A naught. So everything that A is not, if you want to think of it that way. So everything that A isn't, if the A is even numbers, then the uneven numbers would be everything that A isn't. So 1, 3, 5. And together, these two represent all of the possible outcomes. Sorry, there's a cat in the background. So A plus A naught represents all of the total outcomes in this case. So how many are not even numbers and how many even numbers? Well, they're both equal to 3. So the set of A is 3 numbers, and the set of A naught is also 3 numbers. Together, we get all of the outcomes here. This is something, in this case, is very obvious, but it's not always obvious. So we say that if we have this other thing, which is S, S is the set of all the numbers, all 6 sides. I'm not going to write them all out, although it probably would have been the same amount of work. So all 6 sides. So that means that the number in the, if we say the number of all of the elements in S, all of the outcomes, it's really equal to the same number as all of the elements in A plus all of the elements that aren't A naught. That is a useful thing to have, and we've actually already used this idea, but we'll see that more and more, and it's something important to have. So basically, this is just saying everything we just talked about here. Venn diagram's box with circles contained within it, and you've got sets. So you can call whatever you want. Generally, they use A, and then you've got the universal set S, which is everything. S can be written inside or just outside of that box. The actual items in it, the outcomes, are often called elements. And in this case, we've only got one set, or two sets if you want to include a naught. So what is a set? A set is, and you've seen this before, a set is a collection or a group of items. And the items can be numbers, but they don't have to be numbers. So a set can be whatever you want to make them. So for example, you could have set A here be this list of numbers, set B could be these things, and set C could be these things. But one thing that's always used is this S, which is the sample set, or the universal set. And it's really just all of the possible elements you are looking at. So if I was looking at all the students in our class, then the universal set would be the number of students in our class, not the number of students in the school. But if I changed the idea and said, okay, we're going to look at all the population of the school, then that then would become the universal set. That's something we'll see all the time. Sometimes you can have sets with nothing in it, the null set. The null set is often represented by a zero with a line through it like that. Just something to be aware of. Okay, so we had a question that was similar to this before. In how many ways can you draw a red 5 or, oops, I don't know what that was, a red 5 or a heart from a deck of cards? Okay, not everyone's familiar with the deck of cards. So a red 5, you can have the hearts, or you could have diamonds. So you've got two options fitting into the red 5. Okay, so we've got the red heart 5 and the 5 of diamonds. So we've got two options for this one. And if we look at all the hearts, they pop up here. So we've got a total of 13 different hearts in a deck of cards. So if we want to know how many options we have of drawing these, this is where you can think of, and again, it's a simple example, but you can think of this in terms of a Venn diagram. So if I draw my Venn diagram, this time I have two sets. And if you consider the second set, if I look at one set, so let's say these are the 5s. So 5s. And the other set, which is bigger, but I'm not necessarily going to draw it bigger, which are the hearts. In this case, you have one of these elements from each set. So this guy here and this 5 are the same thing. So you end up with this intersection between the two sets. And we represent that in this case as, if I call set A and set B, the intersection is an upside down U. And so when you figure out your total number of options, you have to consider this intersection. So if I look at it as the number of red 5s, which we said are 2, and the number of hearts, which is 13, your total number of options or outcomes is going to be these two things minus the intersection. So the intersection of these two sets. So we have 15 minus the 1 overlap because we've double counted it. If I take 2 plus 13, I've added the red 5 twice, the 5 of hearts rather. So that means I have to subtract it once. This is a general equation that we should know. So the number of any element or set of elements A plus the number of a set of elements B is always going to be the number from each of those two sets. But we have to subtract the intersection because we've double counted it like that. So you can keep that like that. That is going to be something we're going to use. So these two added together, it's really like this. And we're going to change this into the union in a second. So here's the intersection of sets. So let's say I want to have the elements that belong to set A and B are the members of set and members blah, blah, blah. So I've got, let's say, example A, the students in calc, and set B are the students in data. So you do have some intersections between the number of students taking calc and also data. And so the formula, and I'm just going to write it out in more of an official way, if we're looking at just the intersection, the number of A intersect B, that's the elements in both sets. Like that. And this, just to write it down again, upside down U is the intersection. That's a C. So the intersection between those two. Great. And so we could figure that out if we had the numbers. Sometimes we have sets of numbers that are disjoint. So joint meaning together, disjoint meaning separated, so that you have two sets, but there are no common elements. Another way of saying that is that they are mutually exclusive, meaning no common elements. So I'm just going to write that in, no common elements. So, for example, if we take the set of female students in the school and the set of female teachers, there are no common elements between these two. So that if you look at it in a mathematical sense, the number of the intersection between A and B is 0, or their intersection is the null set. So pretty straightforward. The union of sets. Again, there's another way of writing this mathematically. So we have A U union B, and that means that we have all of the elements in A or B. This terminology or is really important. If you ever see or, it's always going to mean the union. So kind of what we had in the example earlier. So for example, if you are drawing a diamond or a queen from a well-shuffled deck of cards, then we would write this as the number of A union B is really, again, the number of A plus the number of B. But again, if they have any elements that intersect, we have to subtract. Like this. So in this example, we have 13 diamonds plus 4 queens, but we have 1, which is the queen of diamonds, that we have to subtract by. And so we end up with 16. So you can represent that using this. And just so you see it, sometimes you have, again, you're still adding all of the elements of A and elements of B. Oops, that's not supposed to have gone out. So A union B, but it's simply going to be the number of the sets minus, in this case, there is no intersection, so minus 0, so it's just the addition of those two sets. Great. Okay, let's do something, do a couple examples. This one isn't too complex, but the next one gets a bit more challenging. So let's say there are 10 students on the girls' volleyball team and 15 on the basketball team. When planning a field trip with both teams, the coach has to arrange transportation for only a total of 19 students. So we've got 15 plus 10. Obviously that's going to be 25, but there are only 19 students. So we're going to use a Venn diagram to illustrate this. So we've only got two sets. So let's say V is volleyball and B is basketball. So there will be an intersection. So we've got V and B. So the easiest way to do this is to, if we want, we can set up an equation. So if we have the number of volleyball union basketball, and we know the equation is number of V plus number of B minus the intersection. So what is the intersection here? If we go back here, well, 10 here, 15 here, we do know this, and that's this 19. So the number of volleyball, they said, was 10 plus basketball is 15. We do not know the intersection, so that's the part we're going to have to figure out. So if I rearrange this, so the number of volleyball intersect basketball, and you can do the math, 25, move it over, that's going to be negative 6, but both sides are negative, so it's going to be 6. So the intersection here is 6. So when we go to fill in the diagram, if I just change the color, the intersection here is going to be this number 6. So that's my volleyball intersect basketball. So if there were 10 students in volleyball, and I've already put 6 of them in this circle of volleyball, I have to do 10 minus 6, which gives me 4. So there's 4 people just playing volleyball and not basketball. I do the same thing here. I've got 15, but I've already put 6 in, so I subtract 6. That gives me 9 girls just playing basketball and not volleyball. And so you can see these values. It's almost always easiest to start with the intersection and work your way out. And we'll see that when we have a more complex example like this one. Okay, this is a classic example with 3 sets. So they've given us these numbers. There are 140 grade 12 students, 52 have signed up for biology, 71 for chemistry, and 40 for physics. The science students, so these students, include 15 who are taking both bio and chem, 8 who are taking chemistry and physics, and 11 who are taking bio and physics. And there are 2 who are taking all 3. How many are taking no science? So there are some students in the grade 12 course, or grade 12 class, who are not taking science. So let's do this. So I'm going to move, I've already made these because I knew it would be so rough to draw them myself. So I'm going to pull these in. You can sketch some on your paper. So I know I'm going to have an intersection. First thing I'm going to do is to write out all of this information. Let me move these actually. So let's write out all of what we're given. So you can, if you want to, you can just read through. So let's say science, or sorry, bio is B, chem, C, and physics, P. So the number in bio is the first thing they give us. It's 52. The number in chem, 71. Number in physics, 40. So we got that information. Then we can, science students include 15 who are taking both. So now we want the intersection of bio, chem. So that's intersection of B and C, which is 15. So that's this part here. Chem and physics, so the number of chem intersect physics is 8. intersection of the last combination, bio and physics, is 11. Then we get this number here, which is 2 are taking all 3. So if we go down, number of bio intersect chem, which is also intersecting physics. So we need 2 intersection symbols. That is 2 like that. So if we want, we can represent this 2 ways. First, let's do it in a Venn diagram. So I'm going to put bio up here, chem over here, and physics. Again, we should start in the middle and make our way out. So the intersection of all 3 is this number. So the intersection where it's all overlapping is 2. Now, if I look at, what's this one? Bio and physics. So this is 11. So this intersection, this whole thing needs to add up to 11 because this is the intersecting parts of B and P. So this whole thing needs to add up 11, but I've already put 2 here. So that means this one needs to be 11 minus 2, which is 9. So 9 plus 2 gives me all of the intersecting parts. If we go to the next one, chem and physics. So down here is a total of 8, but I've already put 2 in, so I put 6. Bio and chem, subtract 2 from 15 gives me 13. Good. So now if we keep moving, the physics, now all of this circle, 9 plus 2 plus 6 must, plus something must equal 40, but it can't go over 40. So I do, if you want to figure it out, 40 minus those numbers, minus 9, minus 2, minus 6, that gives me the total here of 23 who are just in physics and nothing else. We can do the same for chem. So if I do 71 minus 13 minus 2 minus 6, I believe that gives me 50. And same with bio, 52 minus 15 minus 9, which gives me 28, I think, like that. Okay, so this is the whole number of students taking science. So if I look at that, that means that if I add all of these numbers up, it should add up to the total number of the union of biochem and physics. So if I take the number of B union C union P, it's all of these numbers added up. And if you do that, I think, so 50 plus 13 plus 2 plus 6 plus 9 plus 23 plus 28, I believe it works out to 131. And that's the total in all of the circles. So that's one way of working this out. So in the question it says, how many are taking no science? Well, our total number of students in grade 12 are 140. Therefore, 140 minus 131, 9. So that 9 students, I think that's what it asked, doesn't it? 9 students are not taking science. Like that. So that's one way. It doesn't always work so easy given certain information. So there's another way, and I do want to show it to you. And it just uses a formula that stems on what we've already written. So if I say the number of B union C union P, that is the number of all of the bio plus the number of all of the chem and number of all of the last set physics. But I need to, if I added all those up, I've actually double counted in some cases. So I have to subtract, just like before, the intersections. So the intersection of B and chem, B and P, intersection of Chem and P. Now the problem with that is that if I subtract by all of those intersections, I've actually subtracted this middle part one too many times, because I've subtracted this, and then I've subtracted this. What we need to do at the end, which is counterintuitive, is add in the intersection, and I can't write it all in one line, of the three sets. The intersection of, like that. So the formula looks awful, but really it's not hard to figure out. It's the three sets added together minus the intersections of each of the two sets. So you can figure out those combinations. That's not hard. And then you just have to try to remember that you have to add in the intersection of all of the three sets. So if we plugged in these numbers just to double check, so I got 52 plus 71 plus 40 minus 11 minus 8 minus 15, and then add in the 2, and you plug that all in, it will work 131. So you get the same answer if I take that, subtract the total number of students, I get 9. So it's just a different way of writing it. The questions for practice on these are listed on the bottom of the page. If you have any questions, I will be in class